We're back.
Welcome, everybody, to episode 454, where we once again play technical douchebags and tell you that words, in fact, matter.
Yes, I'm going to change over the scene to this one. How's that? Ooh. I forgot. I got to change the buttons on this thing. We have a new way of doing this where it's going to switch back and forth. If you're a video subscriber, you'll see that. Yeah,
let us know. Let us know if you like it, and you should definitely be a video subscriber. So, all right. Well, speaking of seeing us, where else can they see us, Bob?
I tell you what, it's getting a little lean, but tonight, if you're watching tonight on July 18th, 1930 hours, we are hosting with Mr. Mike Hildebrand on the After Action Report. This is going to be, once again, free. It is on Facebook. Comments are on, so interact. By all means, send us some pictures. We'll throw them up there for you. And also the Battery Destroyers episode 3 is in the works, and I believe we're doing that on September 4th?
September 4th is the actual day of the event, and it should take us usually about a week or two to get all of the video edited and posted, and then we'll have an episode about it.
And we have lots of new swag in the HMAF store. So if you check hmaf.pro or even the website, you'll see all types of stuff. We have Continuing Challenge September 3rd and 4th, and then Virginia, September 10 through 13. I believe that's the end of the year.
Yes, it is. That pretty much ends it, since our one of our faves moved to the springtime. So we'll have to wait till January to talk about that one. But as long as we're talking about things, what are we talking about today?
Well, we started that whole words matter thing way back, and we said we were going to revisit it every once in a while when they had a couple of free minutes. And these are terms that are commonly conflated or confused or misunderstood. And so in this episode, we're going to do mixtures versus compounds, and the technique, or not the technique, but the science behind oxidation versus reduction.
Yeah, very similar, often confused, often mixed up. Often it doesn't matter, but often it does.
Yes.
So
words matter in this stuff.
It really does. It really does, because it's when we say all the time when we begin a class, we often say, we're lying to you, right? We're going to be lying to you. And we justify it by saying we're not really lying, but we're making a generalization. But if somebody who was really, really, really knew the subject came in and listened to it, they would absolutely raise their hand and call us out and be like, that's not technically true. And we're like, yes, we know that's not technically true. Well, this is the point in time where something happens, there's misinformation, there's miscommunication, and usually it happens when people mix up the technical terms of the words and are left with thinking they're dealing with one thing when in the reality that they're dealing with the other. So what's the first one that we're going to be examining?
Okay, let's summarize it in real short. When I have a mixture, it's a physical blend retaining each substance's properties. So, for example, if I have like sand and water, water still water, sand still sand.
Even if it's being mixed up and it's heterogeneous and it's all in suspension, the water's still the water and the sand is
So in that case, sand and water, we're talking about a mixture.
Sand and water, talking about a mixture. Now, a compound results from a chemical reaction that's actually forming a new substance. And this new substance has completely different properties that are distinct from the original reaction, and they hold their own, and it can't be separated.
Right. So let's start with mixtures and go through that one and kind of tease that out so we can understand a little better.
Okay, so the technical definition of a mixture is a combination of two or more substances where each one of those substances retains its own chemical identity and property. So if I were to take, let's change it from water to an acid and sand, right? Mm-hmm. And I were to pH this mixture of acid and sand, still going to have the exact same pH as it did before. It's still an acid, and the sand is still a sand. The properties of the sand are still going to be there. If I can pull the sand out, I can mechanically separate the two. So that's a mixture.
Right. And so we can do this in various different ratios, right? The components in a mixture can vary in proportion. Like the fact that I put a gallon of water and 16 grain of sand doesn't change it, or the whole thing's full of sand and I put a cup of water in it. It's still a mixture.
So would this be similar to putting 1 cube of ice in the scotch and 2 cubes of ice? Like, you're still drinking the same amount of alcohol. Nothing of that property's changed. It just has more water added to it.
Yeah, I'll go with that. I like that.
Okay.
Yeah. And as far as the property, each component in the mixture maintains its own properties, right? So like, again, we've done this where we've done the salt and sand, right? 2 solids. We're talking about water and sand, which is a liquid and a solid. You can do this with many different things. In fact, you can do this with gases as well.
Now, one of the things we talked about that helps define the difference between a mixture and a compound is its ability to be mechanically separated. And when we say mechanically separated, there's a variety of different ways that you could go about mechanically separating 2 mixtures. Depending on what it is that is the mixture, you could filter it. You could also evaporate it, which is commonly used for liquids with similar boiling points, but not exactly the same boiling points. If I take whiskey, for example, and I pour it through a filter, it's not going to separate out the water and the alcohol. But if I take alcohol or the whiskey and I put it through an evaporation process, I can physically remove the water and the alcohol. That would still be a physical or mechanical separation. There's no chemical reaction happening in any way, shape, or form. So what are some of the different types of mixtures that are available to us? We have, as I mentioned before, a homogeneous mixture, which is uniform in composite. We can sometimes think of like salt water, ocean water, as being homogeneous. If I were to grab a sample of the water, let's say I have an eyedropper, let's say I have 5 eyedroppers in, and I go to the beach, and I randomly go to different parts of the ocean within a similar area, and I grab pipettes full of that water and I test it. Well, it turns out that the composition is going to be the same no matter where I grab that sample. The other type of mixture is called a heterogeneous mixture. This is when things are non-uniform. You could think of a tossed salad as being a non-homogeneous mixture, or getting back to that sand and water. If I mix the sand up in like a blender or a concrete mixer, I get a homogeneous mixture. The moment I stop that and all the sand follows down to the bottom, I now have a heterogeneous mixture.
Right. And a couple examples of this, as we said, you can have air, which is just a mixture of gases. You can have trail mix, which is nuts and raisins and chocolate and goodness, and then salt water, which is kind of like a solid dissolved into a liquid.
You had to bring up food, huh? Now I'm hungry.
I'm going for it.
All right.
Now we have compounds.
All right. What is exactly a compound then? We dove it into mixtures. What's a compound? A compound is a substance formed when 2 or more elements chemically bond together in a fixed ratio. So here there is a actual chemical change. We have changed the chemistry, we've changed the chemical physical properties. We have a totally new, different substance.
Right. And so the composition of the ratio is always the same. Like water always has 2 hydrogens and 1 oxygen for every one of those things, right?
Right. So it's like it's a whole new formula because we have a whole new product. Right.
And so that ratio, you can bet your bottom dollar it'll be 2 H's and 1 O every time.
So unlike mixtures where we can easily separate them through a mechanical means, we can't do that with compounds, right? If I have hydrogen and oxygen and I put it through a fuel cell and I get water as a dropout, I can't put that water through a filter and easily separate the hydrogen and the oxygen again, because that's a mechanical way. I have to chemically do something to this in order to change it once again. So I can separate the elements only through chemical means. For water, this would be like an electrolysis, right? I have to put electrons into the situation, and that will actually turn around and separate the hydrogen and the oxygen. But that's not a physical action. That is a chemical action.
Right. And then this also kind of points out the different properties. Right. So if I am talking about water, we have hydrogen and oxygen in this thing. Hydrogen is, as the kids say, hella flammable. And then you have oxygen, which is not flammable at all and is a strong oxidizer. Smack these puppies together in that 2-to-1 ratio. And now we have something that is completely different, like water, which has incredibly cooling operations. It's inflammable. It's a liquid. We've changed the properties all around.
Right. So some things that would be examples of compounds, we've talked about water, carbon dioxide would be one, and salt would be one.
Right. So some of the key differences, just to kind of wrap up these two words, is the nature of it, right? The mixtures are a physical combination, while compounds are chemical combinations.
Mixtures can be physically separated, whereas compounds require a chemical method to do so.
As far as the properties, the components and mixtures retain their original properties, while compounds have new properties that are different from the constituent elements.
In my sand-water mixture, I can have any proportion of sand and water that I want, whereas compounds have a fixed ratio of those elements.
Well done. That was a nice one.
I like that.
Sweet. All right, let's move into the next one. Oxidation and reduction, which I want everybody to kind of oh my God, they're going to nerd out on us. I want you guys to understand that without redox, you don't have electrochemical sensors. You don't have chemistry is redox.
Yeah, I think it's really, people are like, oh, well, where does all this come from? Oxidizers, redox, oxidation. They named these terms based upon what they could observe at the time that they were observing it. So an oxidation reaction doesn't mean that it necessarily involves oxygen. But it did when they discovered this type of reaction. When they discovered this type of reaction, they were looking at oxygen in the process. So that's how it got its name, oxidation. But the technical definition for an oxidation reaction is a process in which a substance loses an electron. So an electron is taken from it.
Right. And the reduction is the gain. So let's just define oxidation. Let's start with oxidation and define it.
Yes, oxidation is the process in which a substance loses an electron.
Okay. The electron loss is the side of so everything has a yin and a yang, let's say like that. Okay, so in the oxidation side, we have the electron loss, and that is the substance that undergoes the oxidation lose one or more electrons.
Right. Now, some people have heard in chemistry and through your chemical physical properties something known as an oxidation state. And the oxidation state is basically the number of electrons that element is capable of losing in a stable way. Right.
Now, you can also have oxygen gain, which often involves the gain of oxygen, but not always. For example, when iron rusts, it reacts with oxygen to form iron oxide.
Now, hydrogen loss would be sort of a reverse example of this, and it often involves the loss of a hydrogen atom, but not always. For a good example of this, think of hydrogen peroxide decomposing back into water and oxygen.
Right. So now here's a couple example reactions. When magnesium reacts with oxygen, it forms magnesium oxide. So the magnesium is oxidized.
Right. So you get a loss of electrons. Now let's talk about reduction. Reduction is the process in which a substance gains an electron.
Right. The gain, the substance that undergoes the gain of one or more electrons.
Yeah, this is kind of a tricky thing in chemistry when we talk about, because you talk about a reduction as being a decrease in that state. Right.
It's actually the opposite.
Yeah, it's very much so, because we look at it from the point of view of like, oh, we're becoming more negative. They're like, no, but we reduced it. I'm like, yeah, but I'm adding an electron. You're adding negativity, so you're reducing by gaining an electron.
Right.
It's always something that has to be thoroughly explained during class.
Now, you can have oxygen loss, because we kind of went through the other parts in here. Like, for example, when copper oxide is reduced to copper in the presence of hydrogen, this would be a reduction.
Right. And you can have a hydrogen gain, which often involves the gain of a hydrogen atom, but not always. For example, in the reaction where nitrogen gas, N2, and hydrogen gas, H2, form ammonia, NH3.
So when copper 2, a couple examples, copper 2 oxide is reduced by hydrogen to form copper and water, then you get CuO plus H2 equals C, whatever, it doesn't matter. But the key differences, let's just go through and just kind of summarize.
It's the electron transfer that really is the key differences. I mean, it really is the difference between the two definitions altogether. Oxidation involves the loss of electron, while a reduction involves the gain of electrons.
Right. And the oxidation state, in oxidation, the oxygen state of the substance increases. In the reduction, it decreases.
Yeah. Oxygen is often involved in gaining of an oxygen, or an oxidation is involved in the gaining of oxygen, and hydrogen is lost. Whereas in a reduction, it's opposite. You lose Jesus, I can't speak today. You lose the oxygen and you gain the hydrogen.
Right. And there's a little bit of interdependence on this. In fact, it is a huge interdependence. It is something like really like the yin and yang. So oxidation and reduction always occur in a redox. Reduction, oxidation, reaction. When one substance is oxidized, another one is reduced. For example, in that reaction we were talking about before with magnesium and oxygen, the magnesium is oxidized, the oxygen is reduced. There you have it.
Yeah, don't even get us started with reducing agents and oxidizing agents, because then you really get confused.